Okay, so my talk today is an update on the status of the OpenXT project in 2016. Just to introduce who's talking to you today, I've been involved in Xen and Xen-related projects for a significant amount of time. At the moment, I guess I started 10 years ago with Xen Hypervisor. I worked on Xen Server, Xen Client XT, and most recently, since the beginning of the year, on OpenXT. And for the bulk of 2016, my work has been on defining a governance structure for the OpenXT project, a bunch of charter and documents to describe processes. And I've also been involved in a security review of the software in OpenXT, both the components that we produce ourselves and the body of software that we bring in from open source. So this is what I'm aiming to cover in the talk today. Is primarily going to be a survey of what's in the project and what's going on in the project and what's different about it. So I'm going to cover an introduction to OpenXT. I'm going to try and identify the distinguishing aspects of it and then give you a description of the most recent stuff that has been going on, that's in progress, and that we're aiming to do in the near future. So to describe a bit about OpenXT and give you an introduction to it, I thought I'd start with a description of what motivates people to work on it. This is a bit of a personal interpretation, given that we are a community, but I think this is common to most of the participants in the project. So what we're aiming to do is improve the state of security in a computing platform, when we're aiming to provide a body of software for people to use in order to do that. So it's a collaborative open source project where we're providing a Xen-based distribution that has a particular architecture in support of more secure computing, technologies that are generally commodity available to anybody to use, but deploying the bulk of them in order to make it more robust to partial compromise by defense in depth. That's the key thing, I think, that stands behind what we're aiming to do with the OpenXT architecture. So the technologies, what I'm aiming to do with this slide is describe OpenXT in a single slide with the things that it is. So we use virtualization and Xen to build a toolkit. It's basically a distro that includes everything that you need to get a virtualized system up and running. So we've got the tool chain, the build system, the Linux kernels, the software distributions to run in DOM0, in your VMs. It's extensible so that you can add in your own software at build time. You can add in your own software at runtime through the use of service VMs and APIs. And in the design of all this system, security is a primary criteria in the architecture decisions that we make. In our technology selection, the way that we configure the software stack, how does this impact the security of the end system is a primary criteria. And I think that's a differentiating criteria to some of the other software distributions you could choose to use. OpenXT is all open source. The code's on GitHub. It's got OSI approved licenses. We develop in the open. We have a public mailing list. We have public defect tracker, an IRC channel populated with developers who are engaged. That's the kind of project that we present to the world. And then the final thing I think that is notable about OpenXT is that it's client capable. It's designed to run on desktops, laptops, endpoint hardware, and it has support for all of the devices, graphics, USB, the kind of things that you need to actually practically make use of the system. So that's the fastest introduction to what OpenXT is, I think I can give. So if that's what OpenXT is, what distinguishes OpenXT is also heavily related to this. So I think the distinguishing aspects of what we built are the focus on security throughout the architecture and the selection of technologies. Another major distinguishing aspect of OpenXT is the community that we have around it. We have representatives from a number of different very capable organizations. The people who are involved are experts in security critical technologies, and the direction of focus of the community is on architecture and security architecture for practical deployed systems. Again, another distinguishing aspect of OpenXT is support for client use cases. We are open source. We use OpenEmbedded. We participate in the OpenEmbedded community. That's what we use to build our Linux distro in DOM 0 and our service VMs. We inherit open source components from that project, and so we're motivated to participate in that community as an upstream to make sure the components are the versions that we want them to be. And the final thing I think I draw attention to about this distinguishing about OpenXT is that it is validated integration. It is a complex system to make all of these complex technologies individually that are complex work together as a cohesive whole. But we have done that and made it available, and we validate the result. There is QA applied. It is tested, and the results of testing acted upon and fixed. So you end up with a functioning, integrated system at the end of it. And then we stand in support of that for our derivative projects, the members of the community who take that OpenXT-based software, customize it for their own use cases, and go and build products with it. So the current build product you get, if you were to go and grab the OpenXT source code and build it today and try and make use of it, what would you end up with? You end up with an installable ISO that you can boot. It will plonk the OpenXT bits onto your machine, and that will leave you with a desktop environment that you can install Linux, Windows, guest VMs on. It is it has an architecture that stands more in support of security than your typical Linux or Windows desktop, because we were making use of hardware technologies to that provide capabilities used by the OpenXT system to lock down the environment that you're running your Windows or desktop workload within. The system that you get if you choose to install OpenXT, as I think I mentioned before, is customizable at build time. Through the use of OpenEmbedded layers, you can introduce extra code in order to tune it for your particular use case. It's also customizable at runtime through the use of service VMs and configuration. So as part of the 2016 focus on governance of OpenXT, as a community, we tried to identify what properties of this platform were important to the community participants, so that when we're deciding what particular direction to take with new technology or feature request, we could ensure that we were continuing to make everybody who's already participating happy. And also it helps to describe what it is about OpenXT that we offer. So we have these platform properties that we've described, what it is the OpenXT system tries to provide to users, and ensure that we keep these in mind and preserve these with future iterations of OpenXT software. So we have these documented on the wiki. They're part of the governance. They're effectively under change control there, and it helps describe what's differentiating about an OpenXT system. Okay, so I'm going to try and run through aspects of the OpenXT architecture technologies that we have chosen to use in the OpenXT system, and I think the common theme throughout each of these is the fact that they're in support of a more secure system. So this is a quick overview list of things I'm going to try and cover with you guys in the next 20-30 minutes. Just to give you the end result of this is I hope you've got a survey overview of all the things we're trying to deploy. So I think the first thing on the list there is a important thing to understand about OpenXT is that we effectively are a downstream project from OpenEmbedded. OpenEmbedded is this open source distributed software packaging project that provides you with a way to produce a customized Linux distribution. So they allow you to, through your configuration, assemble all of the software packages that you need and build yourself a distro. And we use it multiple times because we need to build multiple customized Linux distributions in order to build OpenXT. So, you know, we have one configuration for the contents of DOM0, but also subsequent configurations for our stub domains, the installer file system, our network device driver, virtual machine, the user interface VM. And so we iterate through this OpenEmbedded build multiple times in order to crank out an OpenXT build. So in OpenEmbedded, each package is described in a recipe. It tells you where to grab the tarball from, the source URL, the license of the package, build steps. Each individual package, for example, bash or DMID code or whichever utility you need, is described in a recipe, and collections of recipes are maintained in what OpenEmbedded call layers. And a software layer is a Git repository with a collection of recipe files that are curated by a community that maintain that compatibility between those software packages, that keep them up to date, ensure that they all work well together. And that's what builds you a functioning system. So the base OpenEmbedded layer contains the core of a Linux distribution. There are additional layers you can apply on top of that that are not necessarily part of the core, that allow you to introduce additional pieces of software that not necessarily everybody would want. So you can have this stacking of multiple OpenEmbedded layers in order to build a system containing a reasonable amount of software. And downstream layers can choose to override, extend, customize, and tweak packages that are present in the upstream layers. And so the downstream layers benefit from the fact that the upstream layers are maintained and curated and kept up to date, kept patched for security fixes. So it reduces the work of the downstream layer, but the downstream layer participants can contribute to the upstream layer and thereby share their modifications with the widest pool of people. The economics work out well, and the downstream layers get to produce their customized versions of the software, but also benefit from the maintenance of all the upstream components. So OpenXT provides its own layer. That's the structure of our system. And it includes the components that are custom to OpenXT, and it allows us to tweak packages that we inherit from upstream. But we also prefer to assist with the maintenance of packages upstream, because it means that we don't have to carry the downstream delta, and it benefits the wider pool because everybody else is using the upstream layers anyway. So the nutshell is that OpenEmbedded is one of several projects upstream to OpenXT, and we work to integrate our changes to the highest layer appropriate. So this is a quick tour of the layers that are currently in an OpenXT build. The ones at the top are largely the standard OpenEmbedded layers, where very familiar software from any Linux distro would be found. Further down the list, it gets a bit more interesting. SE Linux builds in the toolchain that we use for SE Linux. Meta Intel is a recent introduction that carries the Intel microcode. Meta virtualization is a layer that we are working to introduce soon, which is a layer that introduces not just Xen, but also it has multiple hypervisors within it, but it is a place where if you're choosing to use the OpenEmbedded standard tools and you want to use Xen, Meta virtualization is the first layer that you would start at, and then we're aiming to build our OpenXT layer in beneath that, so that the work that we do on Xen can benefit other people who are interested in using Xen by putting that in the meta virtualization layer. So the work in order for OpenXT to get to that point is to uprev our supported version of Xen. That's in progress at the moment. The other layers mentioned on the slide, the meta security one is interesting. That's a tool provided by Intel that so you run your build, it will scan all of the software packages that you install and check them against the National Vulnerability Database and report which packages you have, including in the build, that have open CVEs, and encourage you to patch them. Meta measured is a layer in support of measured launch. Phil Trecker, who's around, I think he's at the conference next door. I think he's the maintainer for that. And Meta Service VM is a layer to assist with the packaging of a Linux distro as a service VM suitable for deployment in a virtualized system. Okay. So moving on to the next technology component we use within OpenXT. We use the Xen hypervisor and the QMU device emulator. However, we have a large number of modifications to upstream Xen and QMU, which are maintained in a patch queue. And the reason that we have this series of modifications and we can't just use upstream Xen is there are small changes we need to make that have been that are motivated by our secure client use cases. So the list is actually decreasing as Xen, the capabilities of Xen advance and become a better fit for our requirements as we retire some of our requirements. But the kind of things that are currently in our patch queue are enabling and enforcing the Xen security modules. Support for suspend, hibernate, power management changes that we encounter when we do testing on a laptop may need some tweaking versus the version of Xen that we're currently using. We've got some patches that introduce the V4V interdomain communication protocol. I'll come to that later in the slide deck. We've got a few minor modifications to BlockTap2 to add support for encryption and the disk transfer technology that we have. Those will be revised and applied to BlockTap3 in the near future. We've got some cosmetic fixes to the Windows boot graphics, not the kind of thing that's a high priority to upstream, but it's nice to have for OpenXT users. So they're not necessarily things that are obvious candidates for upstreaming, but where they are, there has been work to do so. I think the ACPI and SM BIOS support is one that's now actually upstream. It's a recent decrease. And a very nice thing about this is that with the work that went into getting Xen 4.6.1 into master in the last, that went in the last week, it's got a significantly reduced patch queue versus the Xen 4.3 that we were using before. Okay, the next distinguishing attribute of the OpenXT system is our distributed network architecture, where we move the network interface device drivers into a dedicated driver domain. In the standard default configuration in OpenXT, all of your NIC drivers are in a single network device driver VM. That then exports access to those NICs to the guest VMs. The data path for that does not go through DOM0, it goes directly from the network device driver VM to the guests. The user interface, in order to manage the network configuration, is split between the user interface VM, where we have the standard network manager applet, and the network manager backend is running within the NDVM, where all the bridging and routing happens. So if this is what you get if you install the default configuration in OpenXT. And on this slide, I've used a bunch of words to describe the same thing for people who are not here, so that they can see later. Go ahead.
Go back to slides just for a second. What's
in red? In red, yes. These are the NIC device drivers. They're in red because they're meant to be scary. Yeah. There's the one on the right is actually the Wi-Fi device driver. Very, very scary. Okay. So there's words describing that. The alternate configuration is one where we actually have multiple NDVMs, so you can have a network device driver VM per interface card. And again, the tool stack will support you in doing that. We have configuration instructions in the project documentation. This one is more robust in that you now have VTD enforced isolation between your physical networks. You'll take a performance hit because you're now going cross domains if you're doing traffic between the NICs. And you need additional resources, RAM and CPU, in order to run your NDVMs. But if that's a concern for you, it's a configuration that you can make work. The last point on the network architecture is that we also have support for Middlebox VMs that you can interpose either in between two NDVMs if you have your physical NIC separated, or between a guest VM and the NDVM, which would be the more common case. So the classic example is the VPN interposition VM, where your guest network interface goes out to your Middlebox VM, and that's where your network traffic is in the clear. It goes into the VPN VM, which puts it into a VPN. So your VPN credentials are isolated from your guest. And then the network traffic from this VPN VM then goes to your network driver VM. So everything that goes over that link is encrypted and contained within the VPN. And your device driver VM is similarly isolated from your VPN credentials. Okay, my next topic is the measured launch. This is an aspect of OpenXT where we put Intel TXT and the platform TPM module to work. And the idea is that we use a measured launch sequence where before we execute each piece of software during boot, a hash of that software and any configuration data is extended into the registers in the trusted platform module. And if you make it all the way through your boot sequence, you end up with a set of measurements that are a representation of all of the software that you are running at that point, and these measurements are then used to unlock encryption keys that grant access to the partitions on disk. So the measurements give you the keys unlock your system configuration data, and also the keys for the disk images of your VMs. The point being that if there's been any tampering with your software or your policy configuration, the measurements by the time you complete launch will be different, and you will not be able to unlock access to the data on your disk. So the implementation of this is built upon a bunch of hardware platform primitives. We try to measure everything that's relevant to that. And so if you have trust in those components, you can then have trust in that you only get access to the keys when you're running the right software. So the notable components I would mention that are relevant to this is T-boot is a major one. There's Trousers, the TCG software stack. We use Lux for disk encryption, and we use the AES-NI hardware acceleration for encryption to keep things performant. The measured launch work is actually undergoing change at the moment. I don't think those patches are yet in master, but they're close. What we're aiming to do is just simplify some of the initialization procedure. When you install OpenXT, you have to provision the TPM. There's a couple of reboots at the moment as everything gets established. So we're doing a bit of work in order to simplify that and improve the user experience. But also it's preparatory work for building remote attestation, which is a feature that some members of our community would like to pursue. It's also improvement work towards enabling you to leave the security of measured launch in place across software upgrades, where you would need to ensure that you know the measurements of the system you're about to run prior to actually deploying that software in place. Okay, the next technology we make use of, we use stub domains in order to isolate the QMU device emulator from DOM0. The primary benefit for this is that the QMU device emulator is a complex piece of software with a large attack surface. This technique of putting it into its own domain protects DOM0 from those compromises. It has allowed us to avoid a couple of Xen security advisories. I did want to acknowledge that the support for this does add extra complexity to the hypervisor and the tool chain, but our community's view is that it is worthwhile. The subdomains that we use in OpenXT are a little different than subdomains used in some other Xen projects, in that we use full Linux operating system in that domain. It has a read-only root file system. It's reset whenever the domain restarts. There's no persistent state there. And we've used a reduced Linux kernel configuration in order to chop out as much from that Linux kernel of stuff that we don't need in there. Access control, we have been running with the Xen security modules enabled and enforcing with a specific custom policy for some time now. It's nice to see that the upstream Xen community is getting closer to enabling that in other Xen distributions. We also provide customized SE Linux policies for our DOM0 and NDVM environments. They are, again, enabled and enforcing, which reduces the capabilities of many of the processes running in those environments to try and contain the effects of a compromised piece of software. A next distinguishing aspect of OpenXT is our PVUSB implementation. So this one is hopefully of interest to the wider Xen community in that it's a production quality open source PVUSB implementation. It's got both a Windows and Linux front end and a Linux back end. It's been through the rounds of testing and validation of our 6.0 release. So it is at this point, I think, considered, at least by our community, to be suitable for use in production. And so we would like to encourage other people to adopt it. It's got a structure that's reasonably amenable to use outside of OpenXT. It's got the typical split driver front end, back end, and a relatively standalone policy control daemon that decides when a USB device arrives what to do with it, which VM to assign it to, whether to assign it to DOM0. And it does that by inspecting the USB device to determine what to do.
Is the back end, is that the kernel or is that the user?
I don't actually know.
And have you, are you aware of the PVUSB implementation that you guys have done in QMU as a back end?
Yes.
Okay.
Yes. I think as a general policy, we're trying to avoid incurring additional uses of QMU. Yeah.
That would potentially make it work with QMU. It's not defined on QMU.
It's true.
I think it's right. In this case, the QMU is just like 2 disks, not providing the hardware. The only exposure is actually, so the only downside is that it's a large process. Because usually it shouldn't be a lot safer than actually doing the
Okay. So one of the more unusual things about the implementation of PVUSB that we have is it uses 2 layers of grant references, so that in order to make efficient use of passing data through the ring, reduces pressure on the ring by the grant reference that goes into the ring is a reference to a page containing grant references. But in order to enable efficient bulk transfer of data between the front and back ends. So yeah, my final point is that we would be very welcome to any outside interest in making use of or helping us upstream this code if there's interest. So I've included on the slide a bunch of links to all of our code locations and documentation for anyone who wants to take a look after the presentation. Okay, next component we have that's a little bit unusual is a secure keyboard and mouse input daemon. This runs in DOM0. It handles newly arriving human interface devices. It decides what to do based on the events, including managing the switching of input between different domains based on what's on display. It protects input from being snooped by other VMs. It helps us enforce the screen lock and also manages the mouse scaling when you're running VMs on the local display at different resolutions. Not too much else to say, but it's a necessary component for client virtualization. Okay, the next thing I'm hoping to capture your interest with today is an interdomain communication protocol, V4V. It's been around for quite a number of years now. It originally developed for Xen Client. It has been reviewed by the Xen community previously, and we benefited from that. It's it's got a particular architecture where the hypervisor itself is involved in transfer of data in between domains. The hypervisor performs data copies. And I'll come to why we do that in a minute. It's used by OpenXT and its production derivatives, and it's also, there's a variant of it in use in Bromium's product. So the reasons for OpenXT pursuing its own interdomain communication transport are in pursuit of the security objectives of the project. So it supports strong isolation between domains because there's no shared memory between VMs that are involved in a V4V connection. It also allows us to put a firewall within the hypervisor that enforces rules on which VMs can talk to which VMs. The rules can be set by a third-party domain that's neither party to the communication, and the rules get enforced by the hypervisor. The performance of V4V is good enough that it supports sustained throughput for use cases where we need it. The interface that V4V provides to guests maps nicely to both Windows and Windows and Linux native I/O primitives. So what that means is that to Linux software developers who are familiar coding with the Sockets API, the V4V interface is a comfortable fit for that. The semantics are similar, and fortuitously, the Windows interface is also it's a good fit for the Windows native I/O primitives, which is advantageous. The V4V also provides as its own interdomain communication transport. It is clearly separate from the guest operating system networking stacks, which is beneficial in support of security objectives where you don't necessarily want a networking stack involved in communication or potentially even in the guest at all. And finally, the V4V implementation is a foundation for some of the future work that we intend to do in OpenXT. So I mentioned that V4V is familiar to the Xen community, having been previously reviewed in a round of upstreaming attempts. So these are the limitations that we are aware of that are, they're relevant and valid, and reasons why V4V is not a shoe-in to the upstream Xen distribution. So the current implementation has exposure to resource exhaustion. You can apply denial of service to the V4V implementation at the moment. Now, that's remediable by introducing some constraints. This is work we intend to do, but the reason that this is there is that these things were less of a concern in the original desktop client use case that V4V was designed to address. So it's something we would like to fix, but it's not there yet. The next issue is that our V4V firewall is a basic implementation. It serves the needs of the project right now, but effectively you have to be, it requires you to be running in a privileged domain in order for you to insert firewall rules. It would be nice to allow guests to insert rules to protect themselves. It would be nice to have better handling of large numbers of firewall rules. So we could improve it. There are plans to do so, but it's not there yet. The next limitation, I think, is our Linux device software requires improvement. There's been a bit of a polish lately, but it's a fairly basic implementation. There was work done at Citrix a few years ago to re-implement it that paused halfway through. But as it stands, it works, but it's not necessarily as clean as we would like. The two remaining things on the list are vChan bindings have been asked for during the upstream attempt. So vChan is a interdomain communication protocol that's already present in upstream Xen. So for people who are using that, who would like to be able to benefit from V4V if V4V were to land, would need a smooth transition path. We have not pursued implementing this because we haven't got a use for it, but we may if there's enough upstream Xen community interest in V4V, then that's the kind of thing that we might do in order to support an upstreaming attempt. And then the last thing on the list is documentation. There is documentation in the code, but it could be improved. It could be a better, softer landing for people who are not already familiar with V4V. This slide is a description of concerns that our community might have with other shared memory technologies that don't apply to V4V. V4V is robust to these concerns. These may not be the concerns of the Xen community, but there are people who care about these things, and it's one of the motivators for V4V as its own protocol. So just to run through this, in a shared memory system, you might have peer domains directly tampering with the ring indexes in order to try and confuse the communicating domain on the remote side. With a shared memory implementation, you can't necessarily know which principal wrote the payload into memory. You can't necessarily prevent memory being shared with other domains. The use of Xen store in some shared memory technology where you're establishing your communication path puts Xen store into the TCB, which is a concern that doesn't apply to V4V. So I think my last slide on V4V is the description of the new work. So the new firewall we're looking to build is part of an effort towards a unified access control architecture in OpenXT. One of the things, if you were to look at the data communication path between domains in OpenXT at the moment, you have a number of different policies that and technologies you have to reason about in order to determine whether two domains or two processes in two domains can communicate with each other. If we were able to simplify that by using the Xen security modules and SE Linux, you can take advantage of the standard tooling provided for those to simplify your reasoning about whether you've done everything correctly. It makes catching errors easier. In addition, one of the things that we would like to do is enable the transfer of SE Linux labels across domains so that you can determine and reason it. So an individual process communicating over V4V with another domain, the receiving domain can have a label arrive with that communication, and then it can reason about whether it's talking to the right process on the other end of the channel. It'd be a nice property to then be able to apply, SE Linux access control to make sure that only the communication you really want is occurring. Okay. Okay, so I think that's the end of my talk about what OpenXT is and the distinguishing aspects of it, and moving on to what's been happening more recently. So in June we had our first hopefully annual OpenXT Summit in Washington, DC, with a large group of people from 24 different organizations who are interested in the work that we do, looking to participate and potentially make use of OpenXT. On the software release side, the big event is the version 6.0 of OpenXT. It is in the very near to release state at the moment. It's feature complete. It's no further code change, with the one exception of the final remaining work, which is to enable the clean upgrade from the version 5 to version 6 copy of the software. And the things that we managed to build into version 6 were major uprevs in a bunch of core components. So the Xen hypervisor upgrade to 4.3, Linux kernel upgrade to 4.4.16, which was the tip of the 4.4 kernel tree at the point we locked down. QMU had its build configuration tightened up to harden that. The major benefit of uprevving most of the platform components was the enabling support for Skylake hardware platform. I guess to mention, the core OpenEmbedded software distribution that we use was also upgraded. So this is basically all of the software packages that get populated into the VM file systems. And that was followed by a code-based security review where we went through looking for known vulnerabilities in any of those packages and ensuring that we had included all the security fixes. And then the final thing to make it easier is that we have a new containerized build system that allows you to git clone on a Debian system, and it will populate containers containing the right build materials and enable you to run a full sequence build, including everything. So hopefully we will be able to pull the trigger on the final version 6.0 bits within the next few weeks. Okay, next big development is on project governance. I'm slightly biased on this, having been personally involved in this, but we've got a new set of documents describing our decision-making processes and priorities in the project. They're all publicly available on the wiki. And, okay. The work that's currently in progress. I think I mentioned earlier, we provide an open embedded layer which contains all of the OpenXT software recipes. What we would like to do is separate this out into multiple layers so that if, for example, you have an interest in running a secure headless system that you don't have to build all of the rest of the OpenXT software, you can just choose the components that you need. This has an additional benefit. The addition of layers into the code base allows us to tease apart things that might be potentially conflicting between support for the graphical use case versus the desire to keep the attack surface small and constrained. Those two things might be in tension, and we can address the needs of different groups within our community by pushing those features into separate layers. So if you need the graphic stuff, you can build using those layers. If you don't, then you don't have to bring that extra body of code in. In kind of a similar vein, we're also trying to push code out of OpenXT by just adopting the versions that we can inherit from upstream OpenEmbedded. It's one of the reasons we're also heavily pursuing more recent version of Xen, is that our patch queue is reducing as we're able to get closer to what you guys are doing at TIP. I guess that's the last point. Yeah, the work in progress at the moment. We've just last week landed 4.6.1. 4.7 will be next. Hopefully won't be nearly so much of a big upgrade since we're closer already. The next project that's underway is the refactoring of the OpenXT tool stack to introduce libxl at a lower layer. This will help us ensure that the OpenXT tool stack remains compatible with upstream Xen, so that we'll be able to track libxl along with the hypervisor uprev. But in addition, part of the motivation for this is getting the upper half of the tool stack out of DOM0, potentially to allow us to have pluggable tool stacks so that you could choose which version you want. So that's in progress at the moment. I think that's recently picked up a reasonable amount of speed with an extra engineer on it. Work in progress V4V. You should, come and talk to us about this. There's a bunch of stuff we would like to do. We would like to primarily gauge what the interest is outside of OpenXT with involvement in V4V and potentially upstreaming V4V, or whether or not it's going to remain a primarily OpenXT technology. We've got some enhancements to measured launch, I think I talked about previously. The major thing that we would like to pull off there is the forward ceiling across software upgrades. Another group within the community are looking at adopting upstream Windows PV drivers. That'll have a number of benefits. I don't think there's really any interest in carrying our network and block drivers, but also things like upgrading the Xen-bus driver is relevant to PVUSB. It will enable other people to make use of our PVUSB implementation more easily if we're using a common Xen-bus driver. Okay, the next major event on the graphics side is a whole new graphics display architecture, which should be open source any day now, right? Brendan is going to be giving a talk on that separately at the summit, so it'd be worth attending that. Get an update on that. In the upcoming future that's not currently in progress, there's a group within the community that would like to begin work on integrating Xen Upstream's VTPM manager into OpenXT. I think they're quite keen on doing that. We'd like to talk to the Xen server team and the Xen community about adopting and maintaining BlockTap 3. There's been a few quiet discussions in the corridors already about that, but it's pretty much the plan for OpenXT at the moment is to continue to use BlockTap technology rather than QMU. And then the last piece of work I'm aware of that we should be engaging in the near future is making T-boot into a UEFI module in support of UEFI boot. This is the places on the internet where you can find where we work on OpenXT. If you want to come see what we're up to, find out what's going on. Links are all in the presentation. Thanks for letting me talk to you today about all of our stuff. So, anybody have any questions? Anything I didn't cover or? All right. Hi.
You seem to say the slide that had a lot of the things currently in your Xen patch queue, and you seem to be under the impression that a whole load of them may not be terribly interesting. I respectfully disagree.
Okay.
A whole lot of things like suspend and resume changes, we frequently get individuals coming along to the Xen devel list saying it doesn't work on my one random laptop, and they're not in a position to debug. But if you have already gone and debugged and made improvements, that is.
Well, yeah, it would be interesting. It would be nice just to point them at our ISO to see if they can test it with that, and if that addresses it, that would be a fast way to at least.
To a certain extent, Qubes and Ubuntu have also come along and said we've got random problems with Xen on random piece of hardware. So from that point of view, everything like that, we absolutely do want upstream sooner rather than later if possible.
I think there has been some work to do that. We have a wiki page that describes every patch currently in our queue, along with whether or not there is whether it's judged to be upstreamable as it is, whether or not it would need additional work, whether it's something that we can retire when we upgrade to a newer version of Xen, because you guys have already got it upstream. Yeah, there's not really a motivation for us to hoard patches. Is there a particular thing you would like to see?
No, not especially. It's just I look at that list and most XSM, yes, there is quite a lot of work that needs to happen on XSM before it can be enabled by default, but seeing as you've already done that, maybe you've already done some of the work. The block tap 2 and block tap 3, tap disk 3 stuff, that's all a little bit complicated and we'll need to do something slightly better than simply throwing some patches around. I'm interested in what your cosmetic fixes to Windows boot graphics are.
I would have to go look.
Because certainly even if upstream Xen didn't want the Xen server, probably would.
Yeah, I think a reasonable number of those were inherited either from Xen Client or from NX Top. They've been around for, I don't think there's been a recent piece of development on those, other than potentially forward porting as we move to newer versions of Xen.
Right, okay.
Doug?
So mine's a follow-up to Andrew's. You said there's a wiki page describing the packages and have they been upstream and whatnot?
Yep.
Confluence?
Yep.
What's base on Grassley? Because I've actually looked for that before and have not been able to find.
I couldn't tell you off the top of my head, but I know that I get updates when Michon and Ross work on that page.
I'll harass off.
Yeah. Okay.
It's got a lot of
Yeah. Any more? Neil?
You said that you reviewed that basically the hypervisor copy, or you said domains are a hypervisor copy.
Hypervisor. Yeah.
Okay. So is it structured or just raw data that isn't
It provides a stream and datagram pair of protocols. So the payload would be unstructured. Right? You can put whatever you want between those two endpoints.
So why is that an improvement over using a CRAN?
Well, in order to have that connection between the two endpoints, you need to pass through the firewall in order for that connection to be allowed to be established at all. So, to an extent, the hypervisors can protect a receiving a service endpoint from arbitrary client connect.
Okay, so it's just a binary connection or nothing about the description.
That's right.
Memory function export.
Yeah, you can shovel anything down it. Yeah.
And class doesn't help that over there? Or isn't arbitrary moving the connections to shared memory?
I think, well, I think the XSM control points, don't they, prevent domains from receiving connections between the other domains? Maybe not.
You generically turn off things like granular.
Yeah,
Yeah,
you can't say.
granular
There's no
controls.
granular.
Yeah, and that's, it needs to be.
Right.
The current implementation in 6 is only provides use and send permissions, but not granular, not to say receive or down to data chunks or anything or things like that. That's the future.
Okay, so as it stands right now, what's the advantage of people that it's more granular control than XSM?
Yeah.
There's other issues too, right? Like if you make it symmetric so that, I give you a graph map, you give me a graph map, then now basically the two domains can't be destroyed. So I can't destroy this domain, it's still no background map. I can't destroy this domain, it's still no background map. This is, I think, one of the motivating factors of the B4B in the first place.
I know that was important to Xen Server when they were. I think it was important to Xen Server when they were considering using.
There is a proposal for revocable grants, which is what you guys have, right?
Well, a revocable graph.
They will allow you to do actually revocable grants.
Yeah, that allows a domain to forcibly claim back its resources from a non-cooperative end peer. It doesn't help the domain destruction case though.
But Xen can claim it back on the domain's behalf and destroy it.
county needs to take care of zombie pages that are currently allocated to one domain and mapped by the others, because the only way to do a vertical grant still needs cooperation of the source side. Otherwise, IOMMU doesn't work with that. So there are two separate fixes that need to happen. One is vertical grants where you can pull it back from end here, and one is zombie page tracking in the hypervisor. So a properly dead domain having references moved into the zombie list to allow the resources to be freed on the other side, at which point it will freeze itself up. Just need someone to do that.
There's actually a number of technical details that Leader solves that aren't available.
And probably we're coming up, I know. Tom.
Yeah. No.
Regarding the pages of leaking, I know that in the kernel, the grant alloc driver for the Linux kernel, JWDoc said that there's issues with resource exhaustion, things leaking to the other domain if it shuts down. So yeah, going to what you were saying, it's still.
Well, they don't leak it so the domain can't pop.
Right.
All right. Okay. Thanks very much.